Hi guys, welcome back to In Case of Econ Struggles. Today we're talking about cutoff strategies and using cutoff strategies to find Nash Equilibrium. The game we're going to use for cutoff strategies is called Space Cowboys or Bounty Hunters, so let's talk about the setup. In this setup, we're going to have three bounty hunters A, B, and C. They're all sitting on the couch and they get a text that a new target has been identified, and they are choosing whether or not to get off the couch and go get them or to stay on the couch and ignore it. The cost of going to get the new target is going to be uniformly distributed and independently distributed between 0 and 1. The cost of staying on the couch is, as you might have guessed, nothing. Now you need at least 2 bounty hunters in order to catch this guy. If only one person chooses to get off the couch, you don't catch the target, and that person who got up has to pay the cost of getting up. If at least 2 people go, then everyone shares a prize of 3Z evenly. Everyone gets Z, regardless of whether or not they get off the couch or not, which prevents an opportunity for someone to free ride. So the way this game works is that each of them on their phone get the cost of getting up for that period. Now, independently and privately, they choose whether or not they're going to get up or not. They all find out what everyone else chose at the same time. You find out if you catch the target or not, and then everyone gets the payoff based on that outcome. There are 3 possibilities we need to think about from the perspective of every player. So let's think about as if we are player B. So my 2 buddies, players A and C, might choose to stay on the couch. If they choose to stay on the couch, then I don't matter because I can't catch this guy by myself, so I also want to stay on the couch, because getting that payoff of 0 is going to be better for me than paying that cost and still getting 0 because I didn't catch the guy. Now, if one of my 2 buddies are going to get off the couch, then I definitely want to get off the couch, because I am pivotal. I make us able to catch that guy, and I would much rather pay the cost if I'm going to get Z than stay on the couch and we lose. Now, if both of my friends are planning to go up and to go get the target, then I don't matter because we're going to win regardless, and I can be the free rider, stay on the couch, and get my Z prize for free. Now, the way we're going to solve this, like I alluded to, is we're going to use a cutoff strategy. I know the cost of getting off the couch is uniformly distributed between 0 and 1. So let's say that everyone's playing a threshold strategy where you say, okay, the cost is above a certain value, I'm going to stay on the couch. But if the cost is below that value, then sure, I'm willing to get up off the couch and go try and hunt this guy down. So here is sort of the timeline version of that, or the number line version of that, where I'm going to get off the couch if my cost is between 0 and K, and I'm going to stay on the couch if my cost is between K and 1. Now, because this is a uniform distribution, the probability of each of those is K and 1 minus K. So we can use that to determine how likely each of these 3 cases that we talked about a little bit ago are, and we can use those to calculate expected payoffs. Now, if players A and C are staying on the couch, it must mean that their threshold was below what their costs were, so the probability of that is 1 minus K times 1 minus K, because it's a joint probability distribution. The chance that one of them go and the other one don't, well, that's 2 potential options. The probability that A goes and C doesn't, and the probability that A does not go and C does. So I've added those below here, and that's just saying one of them is below the threshold, the other one is above the threshold. The probability that both of them have cost below their threshold is K times K. Now, here we can use the expected payoff and say, okay, when is the expected payoff of going better than the expected payoff of not going or staying on the couch? Well, here is the expected payoff of getting off the couch with the probabilities of each of those cases and the payoffs of each of those cases. Notice that because we are a high type, we're paying that cost, that theta I. If we are staying on the couch, notice that we do not have to pay that cost, but notice that in that second possibility, if I choose not to go, then we get 0 instead of Z if I do go in the first purple example. So we can use that and we can say, well, when is the expected payoff of getting off the couch at least as good as the expected payoff of staying on the couch? Well, I just simplify that purple expression and that blue equation a little bit, and we can see that if I do some algebra, we'll go through and we'll get to the fact that the threshold, or K, is going to be 1 minus 1 over 2Z. So that means that whatever Z is in the problem that should be given to you, I can use that prize to say, okay, well, my threshold is going to be 1 minus 1 over 2Z. If the cost is above that, I'm not going. If the cost is below that, I am willing to get off the couch and go. This is a best response to everyone else playing this threshold strategy, so it is a Nash equilibrium. Hopefully this gives you a better idea of how a cutoff strategy works and an example of how a cutoff strategy works. If it did, make sure to like and subscribe, and we will see you next time for another case of econ struggles.